Hello everyone, welcome back. Today we're going to be talking about the chapter work, energy and power. So let's start. The first two things that we're going to talk about is work and energy. So these two things are very closely related and we're going to see how similar they are and how we can use them in questions. So let me give you a basic idea of how they work. So the definition of energy is the ability to do work. Now, how I like to represent it is that imagine that you have a wallet, like this is your wallet, and you have about, like, for example, $20 in that wallet. And there's this football, for example, that you want to buy. Now, this football is $20. When you have those $20 in cash in your wallet, you have the ability to buy that football. And when you actually purchase that football, you're actually buying the football. So the ability to buy the football and the ability to have that $20 in your wallet is energy. And when you actually buy that football, that's doing work. That is an example. So we're going to see how these like translate to real life examples, and this is just an example to explain how energy and work are related to each other. So let's get started. The first thing that we're going to talk about is energy. We've talked about its definition, that the energy is the ability to do work, and the SI unit for energy is joules. It's also written as J. Now, energy can be stored in a couple of different ways, and we're going to be talking about the different forms that energy is stored in. And sometimes we're going to just talk briefly about those forms, and other times we're going to talk in more detail because it's included in our syllabus. So, the first form is chemical energy. Now, what chemical energy is? The energy that is stored in foods and fuels in the shape of chemical bonds between like atoms or molecules. An example of this is petrol in your car. The energy is stored in the petrol uh, in the shape of chemical bonds. So when the petrol is burned, that energy is released. Or another example is food that you consume. So there is energy in the food in the shape of chemical bonds, and when you consume the food, it is broken down in your body and it releases energy, which basically helps you stay alive. So chemical energy is the energy that is stored in the form of chemical bonds. The next one is going to be the gravitational potential energy. This is one of the forms which is going to be very important, as there's going to be a lot of examples. So let's try to understand it better. So for example, this is Earth. This is the surface of the Earth, and we've got two balls. We've got ball A and we've got ball B. We can see that ball A is on the surface of the Earth while ball B is at a height h. Now, both of these balls are going to have some gravitational potential energy with them, and this energy is dependent on how much their height is. So, the further away the ball is from the surface of the Earth, the greater the energy of the ball, and the closer it is, the lesser will be its energy, gravitational potential energy. So, gravitational potential energy is basically the energy an object has because of its position in a gravitational field. So ball B has more gravitational energy as it has a higher, bigger H, while ball A has a lower gravitational potential energy because at the height of ball A is much lower. So energy of B is greater than energy of A. We're going to talk about its formula and its question examples in much more detail um, after some time. So moving on, we've got elastic strain energy. This is the energy related to springs and objects that are more bendable. So for example, we've got this spring here. Now, this is just a normal spring, unstretched spring. But when you squeeze the spring, when you push it, the spring contracts and it becomes smaller. When it becomes smaller in this state, the contracted spring has elastic strain energy. And when you pull the spring from both sides, it becomes longer. This longer spring also has elastic strain energy inside it. So elastic strain energy is the energy in an object due to its condition. Work is done on an object to squeeze and stretch it. Elastic energy is saved inside it. An example of this is spring. The kinetic energy, which is another one of the important forms of energy we're going to talk about a lot more, is the energy that moving objects have because of their motion. So the thing that you want to remember right now is that every object that is moving, that is in motion, has kinetic energy, and as the velocity of the object increases, so does its kinetic energy. So if, for example, a car is there's two cars, one is going at 5 5 kilometer per hour, car 1, and car 2 is going at 10 kilometers per hour, we'll see that car 2 has higher kinetic energy. We're going to talk about the formula for kinetic energy and how we can calculate kinetic energy of objects later on. Another interesting form of energy is electrostatic energy, and this is the energy that is stored between charged objects. So if you've got two balls, one is positively charged, the other is negatively charged, there's electrostatic energy between them. Nuclear energy is the energy stored in the nucleus of an atom, and it is released in nuclear reactions, which is a chapter much ahead, and we'll discuss more about this when that chapter comes. Internal energy is also known as thermal energy, or like how hot an object is. The hotter the object, the more internal energy that object has. So this is a very neat diagram which goes over different types of energy conversion. So let's see and talk about all the different types of energy conversions. So, okay, let me just clean this up. Okay, in this diagram, we can see that there's a 4-volt battery connected, and we know that in batteries, there are chemicals storing the electrical energy. So we see that from chemical energy, this energy is converted into electricity, and this electricity then flows through these wires, and we can see that this wire is connected here, and it goes over to this light bulb, and this light bulb lights on. And when this light bulb is on, it releases energy in the form of heat and light. Light is basically heat. So the chemical energy is being converted into thermal energy. We can also see that there's a motor here. This is a motor. When the electricity passes through this motor, we can see that the motor starts moving. So the chemical energy from the battery is converted into kinetic energy here in the motor, and when this motor spins, you can see that it's connected to a line shaft, and this weight also becomes it starts to go upwards. So as this weight goes upwards, its height h will also increase, and so will the gravitational potential energy. So we can see that the chemical energy from the battery is being converted into heat, kinetic energy, and gravitational potential energy. So now we know that energy can basically change its form. So if there's kinetic energy, it can turn into some other kind of energy. This will be very detrimental when we're doing our questions. So let's try to understand this concept like very strongly. So the next thing we have is the principle of conservation of energy. It says that energy cannot be created or destroyed. It is always conserved. If we have energy, we cannot make energy, we cannot destroy energy, we can just convert it from one form to another. So, this is going to help in our questions as well, as we'll talk about this concept a bit more. But now, just to put a basic foundation, let's see this example that they're talking about. So, they're talking about a high level reservoir. High level reservoir is basically, for example, these are two mountains, and you see that there are dams. For example, this is a dam, and behind the dam, water is stored. This stored water is in a high level reservoir. Now, as the high level reservoir is at a height, it's between mountains. So this high level reservoir will have the water in the high level reservoir will have gravitational potential energy, as we can see here. When the dam is opened, or maybe a small gate is opened from the dam, we can see that the water starts flowing out. When this water flows out, it goes through a water turbine. Now, the water as it's falling down, turns the turbine, and as the turbine starts moving, the gravitational potential energy starts to convert into kinetic energy. Now, as the turbines start to rotate, the kinetic energy of the turbine uh, produces electricity, and then we use the electricity in our daily lives for lamps and maybe charging our laptops or maybe driving our cars, some other things, heating. So we can see that the energy which was originally in the form of gravitational potential energy of water was then converted into kinetic energy of the turbines and then was converted into different sorts of energy sources that different sorts of forms of energy that we use in our daily lives. So all the energy which was originally in the high level reservoir, gravitational potential energy, was then converted to one form or the other. Okay, so now it's time we talk about kinetic energy in a bit more detail. As we talked before, kinetic energy is the energy an object has because of its motion. So, the formula for kinetic energy of an object of mass m and velocity v is 1 over 2 mv squared. So, it's 1 over 2 multiplied by mass multiplied by velocity squared. Now, kinetic energy, as we know, all energy is measured in joules. So let's see an example here. It says that calculate the kinetic energy of a football of mass 0.4 kg and speed 20 meters per second. What we do is we simply plug this information into our formula. We know that 1 over 2 is a constant, so we write it as is. Our mass is 0.4 kg, so we plug it here, and our velocity is 20 meters per second, which is plugged in here. When we just plug these um, values in our formula and we calculate uh, it using a calculator or maybe mental maths, we can see that the kinetic energy of the football is 80 joules. So we use this formula to calculate the kinetic energies of different objects in our lives. Maybe it's our cars, maybe some sort of things which are falling or moving. And we'll see different examples while we do the example questions. Next up, we have gravitational potential energy. So, as we talked before, gravitational potential energy is the energy possessed by a body due to its position in a gravitational field. And the formula for gravitational potential energy is m multiplied by g multiplied by h, where m is our mass, g is the acceleration due to gravity, and if we're talking about Earth, it's going to be 9.81 meters per second squared, and h is the height of the object. So an example we have here is that we've got this spherical ball at a height of 30 meters and the ball weighs 5 kg. Now they want us to calculate the gravitational potential energy for this ball. We're just going to plug the values in. So we know that our mass is 5, so we just write 5 here. We know that the gravitational acceleration due to the Earth's gravitational field is 9.81, so we plug it here. And we know that the ball is at the height of 30 meters, so we just plug that information here and we get 1471 joules. So the ball has 1471 joules of energy. Okay, so now that we've talked about gravitational potential energy and kinetic energy, I want us to implement the law of conservation of energy and see that what it means actually. So we're just gonna divide this diagram into three phases. This is phase 1 where the ball is at a height of h. This is phase 2 while the ball is falling, and this is phase 3 while the ball is on the floor. Now remember, conservation of energy states that energy is always always constant. So what that means is we can see here in our diagram on position 1 that our ball has gravitational potential energy of mg delta h, which we've gotten out of the formula mgh. So mg delta h, and as the ball is at rest, it has zero kinetic energy. Now this is simple, it is understood. Okay, so our ball isn't moving, our kinetic energy is zero. and as because it's on a height delta h, it's going to have a potential energy of mg delta h. Now what happens when we drop this ball? When we leave this ball, the ball starts to move downwards. In position 2, we can see that the ball is somewhere in between the height, and at this moment the ball in okay so in moment 2 the ball is moving, so it's going to have kinetic energy, but it will also have potential energy because it's somewhere around here. I don't know what this height is, but I know that it's a height, so the ball will have potential energy as well. So the ball will also have potential energy, gravitational potential energy. Now, how will these two energies compare with the original mg delta h? So in the original picture, we can see that we had mg delta h as our potential energy and 0 as our kinetic energy. So our total energy was mg delta h. So as we know, the conservation of energy states that energy is always constant. So some in this scenario, our total energy is also going to be mg delta h, but it's going to be divided in two forms. One will be kinetic energy and the other will be gravitational potential energy. Now moving on to the third stage, we can see that this is the instant the ball lands. Now at this instant, we can see that the height is basically 0, so our potential energy is 0 and our kinetic energy is mg delta h. But how? Now let's again remember that energy is always constant because of the law of conservation of energy. So our if our potential energy is 0, then our kinetic energy is going to be equal to the original amount of energy. And our original energy was, don't forget, mg delta h. So this is something that you need to remember, that the total energy of an object always remains constant, and at some point it may have 0 kinetic energy and at some point it may have 0 potential energy, but the total energy possessed by that object will always be constant. Now if you want me to put it in perspective, just think of the ball having energy is 10 joules. So in position 1, all the 10 joules is in the form of gravitational potential energy, as the kinetic energy is 0. In the second one, the 10 joules is split up. Maybe 5 joules is in kinetic energy and maybe 5 joules is in potential energy. But in the third stage, we can see that the potential energy is 0. So all the 10 joules will be in kinetic energy. I hope that made sense. So even if it didn't, we're going to do another example. So hopefully, maybe there's something that you can grasp. Okay, so the next example we have is the pendulum example, and this is one of the simpler ones, I would say. So let's start. Let's call this position 1, 2, 3, 4, 5. Now, if you've seen a pendulum start moving, we know that this height is going to be our max height, and this height will be our minimum height. So in the first picture, we can see that in position 1, the ball is at rest and it's at maximum height. So it will have kinetic energy of 0 and potential energy maximum, or we can write it as mg delta h. In the second example, in the second stage, we can see that the ball is moving. Now the ball is moving, so it's going to definitely have some kinetic energy. And as for the gravitational potential energy, we can see that the ball isn't exactly at its lowest point. It's not at minimum height, so it's also going to have gravitational potential energy. Okay, so in the third position, we can see that the object is at its lowest point, the minimum height. So our gravitational potential energy is going to be 0, but the object is still moving. So it's going to have kinetic energy. So that's going to be maximum, or we can also write mg delta h. In position 5, it's the same as position 2, so the object is going to have potential plus kinetic energy, and then in the fifth position, the object is going to be at its maximum height, so it's not going to be moving and it will only have potential energy of mg delta h. Okay, so now we have an example question here. Now I want you to try this on your own. You can pause the video and try it, and I'll just start solving, and then you can compare your answer to mine. And don't worry if you can't, because I'll help you do it now. So it says that a boulder of mass 4 kg, masses are always very important, so we must underline them. Mass 4 kg rolls over a cliff and reaches a beach below with a velocity of 20 meters per second. Calculate the kinetic energy of the boulder as it lands. This is the A part. Okay, so let's start with the A part. So if we want to maybe put it in a diagram, we can see here that we have this hill and our boulder is at the top in the start, and then it goes to the beach at the bottom. Now the boulder, we need to calculate the kinetic energy of the boulder, which means that we're going to plug our information into our formula, which is 1 over 2 mv squared. So it will become 1 over 2 4 into 20 squared. If we just simplify it a little bit, we can find out that it's going to become 400. So our kinetic energy is 800 joules for part A. Now B part, the gravitational potential energy of the boulder when it was at the top of the cliff. Now for gravitational potential energy, we know that the formula is mgh. Okay, so we do know m, we do know g, we need to find what's gravitational potential energy, but we don't know h. Now, is there a way to get an answer? So yes, there is actually. If we just remember what the law of conservation of energy states, it states that the energy is always constant. So whatever the energy the rock has at the bottom of the cliff, it's going to have the same energy at the top of the cliff, except that when it was on the bottom, it had it in the form of kinetic energy, but when it will be on the top, it will have it in the form of gravitational potential energy. So we can see that our A part answer was 800 joules of kinetic energy. So at the top of the cliff, our rock had 800 joules of gravitational potential energy. The C part says the height of the cliff. Okay, so if we just go back to our formula here, we can see that now we have gravitational potential energy as well. We have mass and we have gravitational constant. So we just don't know what h is, and we can easily find that out. So our gravitational potential energy is 800, our mass is 4, our gravitational constant, I'll take it to be 10, and our height is the one that we need to find out. So if we just do a little bit of maths, we can see that we get 800 over 40 is equals to h, and our height is 20 meters, around 20 meters. So this is how you solve questions related to energy. Okay guys, so the next thing that we're going to talk about is work. And as I stated earlier, work and energy are very closely related. So the unit of work is also joules. And work is the measure of energy transfer. So if you remember my example before, I'll repeat it. So imagine you have a wallet, and in this wallet you have $20. Now there's a ball that you want to buy, and it's also $20. Now, when you have this $20 note in your wallet, it means that you have the ability to buy this ball. So I would say that the ability to buy this ball can be represented as energy. And when you actually buy this ball, that's called work. So when you have the ability or the potential to buy the ball, that is the energy that you have. And when you're buying the ball, that is you're transferring that $20 bill into the ball. So that is work. That is an example of, like, putting work and energy into simple terms. So moving on, let's talk about work and how it works. So work is the measure of energy transfer. It is also measured in joules. And the formula for work is equals to force multiplied by distance moved in the direction of the force. So for example, as we can see here, we have We have a box, this red box, and a force of 5 newtons is applied from the left side towards the right. So the force is in this direction, and we can see that the box moves 5 meter because of this force. So the work done on this box is 5, which is the force, multiplied by 5, which is meters, which is distance in the direction of the force. So the force was in the right direction, and the distance moved is also in the right direction. So the work done is 25 joules. Now in this box we can see that this box is pulled towards here with a force of 50 newton, and it moves 3 meters. So the work done is 50 multiplied by 3, which becomes 150 joules, where 50 is the force and 3 meters is the distance moved in the direction of force. Now please note this down. This is very important, that the distance that we use is only in the direction of force. So if for example we have a box like this, and a force of maybe 20 newtons is being applied here, and the box moves towards the right, like for example the after position of the box is like originally it was here, and the after position of the box is here. The work done on this box is 0 joules. That is because the direction of force is towards up, like the direction of force is upwards. This 20 newton force acts upwards, but the box move toward the right. So the distance, this distance is not in the direction of force. This is an example we can see here. We've got a man. This man is holding on to this 3 kg box. Now to keep this box in this place, the man has to apply a force with his hand in the upward direction, just to keep it in place. Now, and the man walks around with the box, but the work done on the box is 0. Why is that? Because the force that the man's hand does on the box is upwards, but the height of the box remains constant. It remains 2 meters. The only thing that changes is its vertical position or horizontal position, like it moves right or left. It doesn't go upward or downward. The box remains in place. The direction of force is upwards, but it remains in place. It does not move vertically. So the work done is 0. This is all for work. Now in questions, we'll see that work and energy are kind of mixed up in questions, and we're going to see how we need to attempt those questions. This was the basic concept, and I'll upload a video for the examples for work and energy later on. In the next video, we're going to talk about power. Thank you for watching. Take care. And if you have any problem, you can type it in the comment section below, and I'll answer. Thank you.